Grade 12 Physics, Fields Note number 6, Magnetic Fields. In this note we're going to actually look at a magnetic field and how charged particles will act in a magnetic field. A charged particle actually acts in a magnetic field. It'll experience a force that's perpendicular to its velocity and perpendicular to the direction of that magnetic field. So this is actually going to cause a particle to perform circular motion. This is something that we're going to look at in class. If we want to look at the actual force to calculate on that particle, the force is equal to Q, which is the charge, multiplied by its velocity, multiplied by B, which is the strength of the magnetic field. If that particle is going through the magnetic field at an angle, the equation turns into F equals QVB sine theta. So that would be sine of the angle that it's going through. F is force in newtons, Q is charge in coulombs, velocity is in meters per second, B is the magnetic field strength measured in Teslas, so that's a capital T for a unit, and theta would be the angle. If we ever actually want to find the direction of that force, it comes from a right-hand rule, which we can use to figure out which direction that force is in. So if you hold your right hand up in the air, and if you point your thumb in the direction of the particle's velocity, you point your fingers in the direction of the magnetic field lines, and remember, magnetic field lines always go from north to the south. That means your palm of your hand is going to point in the direction that the force on this particle will be. So let's use this in two examples here. Let's say some sort of particle has a charge of 15 nanocoulombs. Let's remember that a nano is a 10 to the negative 9 coulombs. It's traveling at 75% the speed of light to the left. There's magnets around it which are 65 Tesla down. It travels through the plates on an 85-degree angle. What force will it experience? So we're going to use our formula here. There's an angle present, so we need to use F equals QVB sine theta. We're going to do the strict calculation, so just by putting in the numbers, and then we'll find the angle after, or sorry, the direction of the force. So Q is put in, so it's 15 times 10 to the negative 9. V, so it's 75, so 0.75 times the speed of light, so 3 times 10 to the 8, multiplied by B, multiplied by sine 85. We get 218 newtons. But the direction here, let's remember our thumb, if we use our paper as a reference, your thumb will point to the left, your fingers are going to be pointing down the page, so your palm is pointing out of the page. That's how we got that direction on example 1. Example 2, let's say we have an old TV where we're accelerating electrons to hit the screen. If the magnetic field strength is 0.855 Tesla, all right, it's into the page. The velocity is 505 meters per second to the right. Let's find the force that those particles experience. So the charge on an electron from last note from milliken is negative 1.6 times 10 to the negative 19. The mass we'll need that for the second part. So let's calculate the force, QVB sine theta. So we put in the charge, negative 1.6 times 10 to the negative 19. 505 is the velocity, 0.855 is the magnetic field strength, sine 90. We get an answer of negative 6.9 times 10 to the negative 17 newtons. And again, with the right hand rule, that force is going to be pointing up. But if it's a negative answer, we need to switch it to positive. So if we switch it to positive 6.9 times 10 to the negative 17, that direction switches to down. So that's the effect of a negative electron. To find the acceleration, we just use F equals ma. So we put our force. The mass of an electron is 9.1 times 10 to the negative 31. We get an acceleration of 7.6 times 10 to the 13 meters per second squared. Now, if we have our charges confined to a wire, so the charges aren't free to roam wherever they want in the magnetic field, if they're stuck onto a wire, the wire itself is going to experience a force. That force will be equal to the current in the wire multiplied by its length in the magnetic field multiplied by the strength of the magnetic field. And if the wire is on an angle, we have to put a sine theta. So F is force in newtons, I is current in amps, L is length of wire in meters, B is the magnetic field strength in Tesla, and theta would be that angle between magnetic field and current. Again, to find the direction of this force, we need to use a right-hand rule. So again, if you hold your right hand up, your thumb is going to point in the direction of the current. Your fingers are going to be pointing in the direction of the magnetic field. And remember again, magnetic fields always go from north to south. That means your palm is going to point in the direction of the force that the wire feels. So let's say we have a wire in a magnetic field, and this wire is going to have the following qualities. All right, let's say it has a length of 1.2 meters. The magnetic field strength is going to be 0.56 Tesla to the right. The angle that it's on is going to be 75 degrees. The current through the wire is going to be 60 amps. That's going to be into the page. Let's find the force on this wire. So using the equation with the angle, ILB sine theta, we put all our values in and we strictly find the value of the answer, which ends up being 38.9 newtons. Now to find that direction, you put your thumb in the direction of the current, which ends up being into your page. You put your fingers in the direction of the magnetic field, which are to the right, and you'll see that your palm is pointing down the page. So that's the way we get that direction. Last one, let's say 3.5 meter wire carries 6.5 amps into the page and feels a 5.2 Newton force to the left. Here, if theta is 90, let's calculate the strength of the magnetic field. So let's rearrange this equation. ILB sine theta, solve for B. Again, we're going to strictly find what our answer is and then try and figure out what the direction that answer is going to be in. So F over IL sine theta. So you put all your values in. Should get a value of 0.23 Tesla. And here, your palm is pointing down. Your thumb should be pointing into the page, so we get your fingers pointing down.